Good morning, everyone, or good evening for some of you, depending on where you are in the world. My name is Darian Wilkin. I'm a solutions engineer here at DigitalOcean, and I'm here to talk to you today, as you can see, pardon me, about requests, limits, and autoscalers in Kubernetes and how they sometimes do not work together, but generally they do. So let's first talk about a little bit about a Kubernetes node itself, right? Now I know this requires a little bit of understanding of Kubernetes, and I hope we're all there, but certainly we can take questions afterwards. So this is generally how Kubernetes sees a worker node. Now this is a DOKS node, so this is DigitalOcean's Kubernetes service. And you can see we have some reserved memory and RAM, or memory and CPU down at the bottom there. That's for the system processes like Kubelet, Cilium, things like that. Most managed Kubernetes offerings will have some reserved resources for these specific services so that they can keep the cluster healthy. But what about the unreserved resources, right? So we've got this little chunk that's reserved for the system processes, and then the rest of the worker node is obviously free for our application, our pods, whatever we want to put on there. So how do we put the right number of pods on a worker node? Well, we set limits and requests in Kubernetes. The, pardon me, the pod's limit is the maximum amount of resources it can use, and the request is the minimum it should be allocated, all right? So Kubernetes pays attention to these, especially the minimums, when it's looking at scheduling. It really looks at the minimum needed, the request, and then it places pods based on the available resources on the node. But what does the available resources look like? Obviously, we know what memory looks like in terms of available resources. Do we have 3 gigs, 4 gigs, 4.5? How many gigs of RAM, right? That's how we measure memory. However, CPUs measured a little differently in Kubernetes. Pardon me. CPUs measured a little differently in Kubernetes. Instead of just looking at the CPU as one big thing, we separate it into what are called millicores. All right, so this is a 4 CPU droplet, and a worker node rather, and you can see that that Kubernetes sees this as 4 CPUs, and I would have drawn 1,000 little squares per CPU there, but it took a little too much time, so I figured you guys could imagine that each one of those CPUs was split into 1,000 different little millicores. So when Kubernetes looks at the requests value, it's looking at how many gigs of RAM or megabytes of RAM do we need, and how many millicores of CPUs, or you can use full CPUs in your measurements, but millicores is what we'll be talking about today, because that's where you can get into some trouble. So to understand how that works, we should first understand how it is that Kubernetes divides up these millicores, right? So a millicore is obviously 1/1000th of a CPU. What does that mean? 1/1000th of a CPU, like in perpetuity? Does it mean one, like we chop up a CPU and there's actually a couple of transistors that we've got? No, it's time multiplexing. What does that mean? It means that the way Kubernetes discerns between allocations of a CPU is in 100 millisecond chunks. And so we'll change the units. I know it's going to be a big flashy change here. Boom, milliseconds, right? So what we get here is that we see 10 millicores is equal to 1 millisecond, right? So 1,000 millicores is equivalent to 100 milliseconds, all right? So this is done by the completely fair scheduler, or CFS. It doles out the resource usage based on the requests, and this is kind of the way it looks. If we have on the top, that's what a 1000M or 1 CPU request looks like, right? Taking the whole 100 millisecond chunk every 100 milliseconds. However, we can see the second line there, we've got a 500M request, and that's only using 50 milliseconds. So maybe that red on the second half is a different process that's using that section of resources. I should note that if the resources are not reserved or requested, then other applications, the pods are able to go over their allocation of CPU and use the extra. I apologize. So this is what it looks like back to back to back to back. It makes sense. We have 100 millisecond chunks. We have them again and again and again, and that's how the CPU is provisioned. So what does this mean in terms of our request value? What should we be setting as our request? Well, it should really be your request size should be greater than or equal to the max execution time of the pod you're setting the request for, times 10. Why times 10? Because we're converting into milliseconds, right? Or we're converting into millicores from milliseconds. So if your longest running process on a pod typically executes instructions for 50 milliseconds, you should set requests to at least 500 M. Hope that makes sense. We'll explain why in a second. Because CPU is a compressible resource, so compressible means we can add more CPU to a node than it has in requests, and the scheduler will try and break up the request based on those requirements. So let's talk about why it is that you want this request to be larger than or longer than your longest process. So this is a 500 M request that I wanted to take as an example. You can see that it gets 50 milliseconds of a 100 millisecond chunk in the processor. So if we have a 40 millisecond process, perfect, we're golden. This looks great. The process executes. It has maybe some extra CPU time. So if it takes a little longer than normal, then that's fine. And we're done. But what if we change that request to 25 M or 250 M, sorry, 25 milliseconds, but we still have that same 40 millisecond process? What do you guys think happens? We'll do a little Blues Clues thing. You guys answer yourselves and then we'll talk about it afterwards. What actually happens is it loops essentially. It has to wait, that process. If the rest of those CPU cycles are claimed by other pods, this process has to wait until the next 100 millisecond cycle spins around, and then it can run the rest of the process. It's essentially paused until that next 100 millisecond cycle comes along. So we've turned a 40 millisecond execution time into a 115 millisecond execution time. Now, you don't need to be a math whiz to see that the smaller you set this request value, pardon me, the smaller you set this request value, the more times this 40 millisecond execution process is going to have to loop. So you can get to a point where you set a 10 M request and it gives you 1 millisecond per loop. And we're talking about 40 milliseconds plus 99 times 40, right? Milliseconds. So you can take 4 minutes to run a 40 millisecond process if you set the request value too small. Let's talk about RAM real quick. This one's pretty simple. RAM is an incompressible resource, right? When we talk about how many gigs of RAM are available, that's a solid number. We can't say, oh, well, we'll stretch that, right, without adding more physical RAM. So, or swap. So there is one big rule for setting RAM requests and limits. It's limits equal to requests. That's it. Pretty simple, right? We don't want we don't want Kubernetes to try to allocate more RAM to a pod than exists on that pod. So limits equal to request for RAM. For CPU, it's longer than your max execution time. And why I mentioned this RAM thing is that obviously the killer triggers for Kubernetes. Now, killer triggers for both Kubernetes and for the operating system of the worker node itself. And a lot of times the operating system for the worker node itself is quicker to trigger the killer on its node before Kubernetes even realizes that it's over allocated RAM. So you can have situations where pods are terminated because they're killed by the operating system of the worker node rather than Kubernetes. That's not what we want to see. So we always want to set limits to requests for RAM in almost every case. So let's talk about then, we've talked about these limits and requests. Let's talk about how they are actually used by the autoscalers. So there are 3 kind of musketeers in the autoscaling conversation. There's the horizontal pod autoscaler, the Kubernetes scheduler, and then the cluster autoscaler. So let's talk about these in order of how they kind of trigger. First, we got the horizontal pod autoscaler. This is a service that creates additional pods. It watches pod metrics, and you can specify which metric it's going to watch. It watches pod metrics to determine when you need more pods. When it determines that you need a new pod, it does not actually place the pod. All it does is go to the Kubernetes scheduler and say, hey, I need a pod anywhere. Give me a pod somewhere. So Kubernetes scheduler then takes that pod and it looks at worker node utilization and requests. Okay, and primarily it's looking at requests. It places that pod on a node based on the availability of resources, RAM and CPU, right? Based on the requests and limits we've set. Then, however, if it cannot find space on a worker node in the cluster, instead, it will call the cluster autoscaler and say, hey, I don't have enough space for this pod. I need a new worker node. Cluster autoscaler then creates a new worker node, which can be placed with pods. So these are the three musketeers. That's kind of how they work together. So here's the basic idea. If the Kubernetes scheduler sees a worker node has free capacity, aka unrequested resources, it'll attempt to schedule pods there. However, if that free capacity doesn't actually exist because the pods are using more than they're requested, they're using up to their limit, Kubernetes will temporarily throttle CPU down or trigger the killer on a droplet to destroy non-system pods. System pods are protected, obviously. The horizontal pod autoscaler, on the other hand, only triggers when pods in a deployment pass the horizontal pod autoscaler metric on average. Okay, the cluster autoscaler only triggers when Kubernetes says it can't schedule pods because they're insufficient claimed resources. Right now, I know this is basic to some of you, and some of you are like, "Where is he going with this?" I promise there's a reason. Why did my cluster fail to scale? This is kind of the catch. So, if a pod isn't sending metrics or it isn't yet ready to send metrics, that the horizontal pod autoscaler does not ignore that pod in its calculations, right? Remember, it's looking at cluster metrics and looking at average metrics across the fleet. The horizontal pod autoscaler does not ignore that new pod. It actually adds it into its calculations, but the HPA says, hey, it's not stood up yet, so it's using 0% of its available capacity, right? The problem with that is we're working on average metrics here. Now you get why they do that, right? We don't want to have a bunch of pods standing up and not calculate for that in our scaling metrics. We want to prepare for the upcoming pods rather than just schedule infinite pods while we're waiting for one to come up. But because the horizontal pod autoscaler measures on average the resource usage of your fleet, of your cluster, each not ready or not sending metrics node is going to drag down the average utilization of your fleet. So this means that if pods are getting stuck in this starting state, then they are making your HPA think that your resource usage for your pods is going down, when actually you've got a bunch of pods who are not contributing at all and a bunch of pods who are full up, who are 100% utilized, right? But because the horizontal pod autoscaler doesn't realize what's going on, it doesn't try to schedule any more pods. So you're not trying to scale anymore. So because it's never scheduling more pods, Kubernetes never creates more worker nodes because it doesn't think it needs more space. So why do those pods get stuck in those states? CPU requests so small, it can take them literally hours to start up. Pods have some startup time. If they're only allocated 1 millisecond per 100 millisecond cycle, it's going to take them a while. It's going to take them a long time to start up. And the whole time they are starting up, they are not contributing to your cluster's resource usage at all. Memory limits are another problem. You can cause instability in your cluster by triggering the killer too much, right? If you set limits for memory way higher than requests, you will constantly fill up nodes. Those pods will use that memory almost always. They want to, but you will fill up nodes super quickly, and the trigger is going to trigger constantly. You're going to have pods that are super unstable. Limits equal to requests for memory. So I have some recommended resources here. Henning Jacobs has a wonderful presentation on all of this that is a lot more intelligent than my look at it. He's a person I initially learned this stuff from. We also have some links here to some bug pages and some details about the HPA algorithm and things like that. Hopefully we'll be able to get these resources out to y'all in the Discord afterward. Excellent. that is pretty much it. So I see we have a question from the audience. So I'll go ahead and, excuse me, read that out. Let's say I want a virtual machine where I can have my website, store some data, install some Windows programs, etc. What components under DigitalOcean do I need? Absolutely. So when we talk, the key there, and the key I want to touch on there is the Windows programs, right? DigitalOcean, as a matter of course, right now only offers Linux machines. Now, it's totally possible to run certain types of Windows applications like .NET applications on a Windows machine. So that's, or on a Linux machine, I apologize. So that's totally possible. It depends on which Windows applications you are looking to use. So that would depend on, but in general, I would say that if they are Windows applications that run on .NET on Linux, then certainly you can use DigitalOcean, and I would recommend you start with a droplet. The specific image of the droplet could depend on your familiarity and other things. Ubuntu is a great one to start with if you don't have any idea what you're looking for. It's good, one size fits all. Awesome. Okay, any other questions that we have? Just give a couple minutes here in case anybody has questions. But yeah, so this actually came up for my team because we had some customers who were pretty upset that their clusters were taking so long to function, to spin up. They were getting stuck in bad states where no pods were standing up. And they couldn't figure out why the cluster autoscale. That was really the initial trigger for this. Was we had a customer we were working with who could not figure out why the cluster autoscaler wasn't triggering when they had such high usage on so many of their pods. And it took some digging for us to figure out that this could be the cause. And in fact, they were setting a 10M request for pods, which is that 1 millisecond per 100 millisecond chunk. And that was causing their pods to get stuck. And as a result, entire worker nodes were sitting there unused, even though they had a bunch of pods allocated to them that were trying to stand up. Because at that point, the CPU was just totally pinned to 100%, because everything was trying to use 1 millisecond per cycle, and nothing was moving as a result. And we got another question. It's, how do you know how much memory you need for requests? So great question. So we can actually go back to a previous slide here to talk about this. Oops, sorry. So obviously each application is different, and various applications are memory hungry, or maybe not memory hungry, maybe they don't use memory at all. But whatever your application's memory requirements, when you are setting limits, and you should set limits, you should always set limits for pods if possible. When you're setting those limits, they should be equal to requests. Beyond that, it just depends on what level of resources you have available versus the specific requirements of that particular application, right? But yeah, if you see on this page, we talk about the idea that if a pod requests 1 gig, but has a limit of 2 gigs, it can be on a node with only 1 gig available of RAM, right? Or maybe 2 gigs available of RAM, and then it tries to use all 2 gigs, and suddenly a new pod gets scheduled, and suddenly its process is killed, and hopefully it can recover from that. But if not, then you've just got a pod that has to be restarted. And then you can get into this terrible loop where you have 2 gigs free of RAM on a worker node. You assign a pod there. It's got a request of 1 gig, and that's all the scheduler looks at, but it uses 2 gigs, right? It's got a limit of 2 gigs, so it uses 2 gigs. Then another pod tries to get scheduled because the scheduler sees 1 gig free, even though it's not. So it kills that pod dies. That new pod starts using 2 gigs. the new pod that is replacing the old pod gets placed on the same node, kills the old pod. You can get into a loop of pod placement where they're constantly failing. It's a really vicious cycle, and it's one of those things that's really hard to track down. It's hard to figure out why this is happening, what's going on, if you don't understand where to look. And limits and requests are a key place to start if you're having problems like that with your worker nodes. Any more questions from anyone? I think we got a few more minutes here. What else can we talk about? So yeah, there are a lot of resources here. Like, so one thing I want to mention, actually, this is a good topic to talk about for the last few minutes. This thing called the vertical pod autoscaler. So we talk a lot about, in one of the old features of Kubernetes is the horizontal pod autoscaler, or the HPA. The horizontal pod autoscaler is great. It creates additional pods for you, right? But what the vertical pod autoscaler does, which is something that's relatively new and still, people are still figuring it out, but the vertical pod autoscaler actually intelligently scales the limits on your pods based on the resources that they're actually using. Kubernetes in general, it does not care about that. It doesn't actually care whether or not the pod makes use of all 500 millicores that it's getting allocated. The vertical pod autoscaler will track how much CPU, how much RAM it's actually using, and right size its limits and requests to those levels. Super useful. Actually, that's a great question. That's a great answer to the question we had before. Probably should have mentioned it. Absolutely, you can use the horizontal pod autoscaler or the vertical pod autoscaler to see how much memory you actually need. One thing I was looking at as a solution for this as well was liveness probes. As you can see, there's a link here for that. So what one thing that can do is help track the specific state of your pods at every point, right? Make sure that you understand exactly when certain things are happening to them and what's happening to them. I haven't configured this myself. Obviously, once you've figured out this issue, you can troubleshoot this particular problem. Liveness probes are a good idea in general, I think, if you have the extra time to implement them and extra resources, but certainly not my area of expertise. Yeah, I can tell you this type of stuff, there's a lot of little tricks with Kubernetes, in terms of how it schedules things. How really the tricks come in the intersectionality, right? In the intersections between the different applications that service Kubernetes. In this case, the complexity arises from the interaction between the horizontal pod autoscaler and the Kubernetes scheduler, right? And then the cluster autoscaler in some cases, when we see the cluster should be scaling up, but it's not. That's often a common lead indicator for that there's that there's a problem. Just looking at, yeah. So so last thing I want to say, and then we'll wrap up here, is that one way to diagnose this is happening. Obviously, if you're having pods that are having trouble getting stood up, that's an easy way to diagnose this is happening if you have a bunch of pending pods stuck on a node. But one easy way is just to look at node utilization. So you can actually look at if all of your worker nodes are 100% utilized and you are not seeing new nodes stood up, new worker nodes stood up, that's a good indicator that this could be a problem, because your HPA is potentially trying to stand up a bunch of nodes and it thinks that they are servicing the application on average, but they are not. So look for high resource utilization without another worker node being added. That's definitely a thing. Somebody asked, there is also a 100 pod limit on nodes, no matter what size the node is. Is this configurable? is I think this is a DOKS limit. And I believe this is absolutely configurable on your own personal Kubernetes. Mostly everything with Kubernetes is configurable. It's like Linux in that if you want to, you can do pretty much anything with your own custom Kubernetes installation. It's just a question of whether or not you understand what you're doing. So I don't know where the configuration in particular is for the 100 node limit, but I absolutely think that's configurable on custom Kubernetes, and it may be a limit we can raise on DOKS for a specific customer. So send in a support request if you're having trouble with that. But awesome. I think that's all we have in terms of questions, and I've certainly talked y'all's ears off enough. So thank you so much for paying attention to me this morning and listening to me drone on about autoscalers and HPAs and things like that. It's been a pleasure, and I hope that you guys are having a wonderful time at Deploy. And I look forward to talking to y'all again at some point in the future.